our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are both from Civil Engineering Department of IIT Kharagpur. We have divided this course into two parts: environmental chemistry, the first part that will be taught by me, and the second part, that is environmental microbiology, will be covered by Professor Sudha Goel. Now, I already discussed in my first module the acids, bases and salts. In the second module, I have discussed about the chemical kinetics. In the third module, I have discussed the chemical kinetics. In the second module, I discussed about the chemical equilibrium, and in this module I am extending the chemical kinetics, but I am discussing about the mechanisms and the catalyst, which are also under the scope of the chemical kinetics and very important topic today. So, this is my module 4 and 19th lecture. This is the chemical kinetics, this is the catalysis I will discuss, and this is the part B. In my last lecture I discussed about the catalysis, but that was part A. Now, all of you know that catalysis, I already discussed that catalysis is very important for us. We have to develop very new catalysts for different types of reactions, and the contents of this lecture is the mechanism, how it is happening for homogeneous. I already discussed what is homogeneous catalysis, what is heterogeneous catalysis, and what is biocatalysis, that is enzyme catalysis. And here I will tell you the mechanisms about those catalysis, how the reaction is going on and what is the activation energy, all those things I will discuss here. Now, mechanism of catalysis. First I will tell you about the homogeneous catalysis. So, here one example is given. This is the thallium, thallium plus, it is an aqueous phase reaction and it is a redox reaction. You see thallus is going to thallium plus is going to thallium 3 plus, and cerium 4 plus is going to cerium 3 plus. So, it is a redox reaction, this is oxidized and this is reduced, and this is the balanced equation. Now, the possible pathways we have to, I already told you about the mechanism. So, now at least we can think about the possible pathways. So, we can think about a single step mechanism. Okay. If it is a single step mechanism, here the positively charged ions collide simultaneously in the aqueous phase to give the product. Okay. So, collision is necessary. If it is a single step process, then it will be thermomolecular reaction, and we already know now that thermomolecular reactions are not very common. Then what is the alternative mechanism that we can think? So, we can think, instead of single step mechanism, we can think about a stepwise mechanism. What is that? This is the first step. Say for example, thallium plus cerium 4 plus is giving thallium 2 plus. This is an intermediate because it is not appearing here. Okay. Thallium 2 plus is not there. So, even if in one step we think that it is produced, so we have to think another step where it will be consumed. So, it is an intermediate, and then cerium 4 plus is going to cerium 3 plus, but this reaction is very slow. Okay. And we can think of in the second step the thallium 2 plus, which is the intermediate, is again reacting with cerium 4 plus to give thallium 3 plus and cerium 3 plus. So, this, if we combine these two, then we will see that it is coming, but this is a very slow process. Okay. Now, if we add silver plus ion here, then we will see that the reaction, we can think the mechanism in this way, then we will see that reaction becomes faster. Okay. at least much faster than this one. Okay. What is happening, if the silver plus ion is added, then this is the reaction, it is a fast process, this is a reaction, and then silver 2 plus is produced and cerium 3 plus is produced. So, silver 2 plus is the intermediate, okay, and then silver 2 plus is again consumed and silver plus is going back. It is an intermediate stage of the, this is a catalyst. So, it is produced from the catalyst, but catalyst should come back to its original position, that I told you. So, even if it is changing, but it should come back to its original state again. So, this is the second step, slow process, and then the last step, this is again fast process. So, thallium 2 plus plus cerium 4 plus, this is the intermediate. So, it should be removed, means consumed. So, again thallium 3 plus is coming, cerium. So, if you combine these two, then you will see that it is coming here. Okay. So, this is a mechanism, and this is a homogeneous reaction, homogeneous catalysis. Okay. This way we can think of. So, for when you think about catalyst, then catalyst should come back to its original position. When you get some intermediate, that also should be produced, but it should be consumed, and you should get finally the after combining all the reactions, how many 2, 3 whatever may be the reactions you think of, then finally it should give you the final means matching actual reaction. Now, intermediate compound theory for homogeneous catalysis. So, this is a theory that is given for the homogeneous catalysis. What is that? The catalyst combines with one of the reactants and forms an unstable reactive compound, okay, called the intermediate. This intermediate compound then reacts with other reactant to yield the products, and catalyst is released. Okay. Similar thing we have seen in the last example, right. Here it is molecule, it is also in chamber process that I already discussed, the sulfuric acid synthesis, where nitrogen oxide is used as a catalyst. Here it is nitric oxide, it is shown. So, nitric, you see this is the main reaction, sulfur dioxide reacts with oxygen to give sulfur trioxide, this is a reaction. Okay. Now, for this reaction NO is used. So, NO is used as the catalyst. Okay. So, NO, how it is acting as the catalyst? By forming some intermediate. What is that? NO first reacts with the oxygen to form NO2, okay. This is an intermediate, and then NO2 is reacting with SO2 to give SO3 and 2NO. So, it is you are getting back that catalyst, okay, regenerated, catalyst is regenerated, and then finally SO3 is reacting with H2O to give the H2. So, it is the synthesis of H2SO4, industrial level, industrial scale, okay, industrial synthesis. Now, so you can see here that what is written here, intermediate compound. So, it is an intermediate compound, okay, compound here, okay. In the last case it was ion, here it is compound. So, some intermediate should be formed, okay. In the homogeneous catalysis, this is the common mechanism, okay. A catalytic reaction consists of several steps. These form a catalytic cycle. So, when there are several steps, so all steps if you think together, it is a catalytic cycle. Although the catalyst change during the catalytic cycle, it returns to its original form at the end of the cycle. Other examples are acid and base catalyzed reactions. So, I will show you some acid and base catalyzed reactions. What are they? Say acid catalyzed reaction, the general way it is shown, and kinetics rate expressions is shown here. Acid catalyzed aqueous phase reactions are very common, it is really common. I have already given you some examples, right, like the cane sugar hydrolysis, okay. It is the it is catalyzed by H plus, hydrolysis of cane sugar to form glucose and fructose, that I told you. So, here you see A is giving P. When A is giving P, it is catalyzed by hydrogen ion, that is acid, okay, and but acid NH plus is staying back as same NH plus. Now, if you think about the rate expression, so minus dCA dt is Kh, this is the rate constant, H plus to the power n and Ca, but this catalyst. So, as it is seen in equation 1, the H plus ion is acting as a catalyst and it is not consumed. So, H plus can be considered as constant, then equation 2 can be written as this one. So, this one and this one can be combined and this is K observed. Okay. So, it can be considered as pseudo first order reaction. Acid catalyzed reaction is pseudo first, here it is pseudo first order reaction, but you can do this. I already discussed this type of thing when I was discussing the kinetics. Okay. So, here you can see that K observed is this one. So, K observed taking log, you can get log K observed is log K H plus n log H plus. So, if you do the vary the pH, then you can get and if you plot and you can measure K observed, then you can plot it log K observed versus pH, then we can get the value of n from the slope. Okay. So, this can be done. Now, base catalyzed reactions also similar, but here it is OH minus, just like the acid catalyzed reactions described earlier, we can write minus dCA dt is nothing but KOH into OH minus to the power n, concentration of OH minus to the power n into Ca or dCA dt minus, of course, minus is written because it is A reactant. So, K observed into Ca and K observed is nothing but KOH, OH minus concentration to the power n. So, taking log both sides, we can get this equation and we can we know that that minus log OH minus log of OH minus concentration nothing but pOH. So, we can in terms of pH you can write this one because pOH is nothing but 14 minus pH. So, the sign is changing here. So, this way we can get this K value also, that n value also. Now, what is the mechanism for heterogeneous catalysis? This is very interesting. You can see here the diagram here. Heterogeneous catalysis is mainly explained by adsorption theory. Okay. So, adsorption is the one step that should occur. Okay. Now, solid surface, mostly heterogeneous catalysis, the examples you have seen, that solid surface, right, solid surface as a catalyst both in gas phase and liquid phase reactions. I have given already some examples for this type of reactions. So, here is another reaction, another example. What is this? This is the, what is this? This is the ethylene. Okay, ethylene. Ethylene means some double bond is there and some hydrogen is added onto this double bond to form the ethane. Okay. This is gas phase reaction. In the gas phase, without any catalyst, the reaction is very slow. However, in presence of platinum as the catalyst, the reaction speeds up. How it is happening? How it is happening? It is happening in several steps. What is happening? Dissociation of hydrogen to hydrogen atoms attached to the platinum surface takes place. So, first hydrogen is attached and then it is dissociation is happening. So, it is the hydrogen molecule, you can see here in the gas phase, this is the ethylene molecule. So, first hydrogen and ethylene both are adsorbed on the platinum, this is the platinum surface. So, both are adsorbed, then it is hydrogen atoms are produced, then hydrogen atoms are added up, in the stepwise addition is happening and then the finally the ethane molecule is going out. Okay. The reaction is going on here, but finally it is dissolved from the surface of the catalyst. Okay. Then again new molecules are getting the chance to get adsorbed and then again reaction is going on, then again the product is going out, like this it is a catalytic cycle that is happening. Okay. So, hydrogen atoms then add sequentially to ethylene molecule and ethane is formed, then ethane is dissolved from the platinum surface to leave the surface free for further reaction. So, this way the heterogeneous catalysis, it is based on the adsorption theory, it is explained. Okay. Now, how does a catalyst makes a reaction faster? I told you already that by it goes through another route actually, that way. Okay. Now, this is the Arrhenius equation you already have seen when I discussed the chemical kinetics module 3. Okay. So, this E A is the activation energy. So, activation energy is lowered in a catalytic means when it goes through a catalytic process by using a catalyst, then this is the reactant, this is the product, it remains the same, the position of the reactant, position of the product is same, but without catalyst it goes in this way and with catalyst it goes this way. So, activation energy is reduced. Okay. So, it becomes faster. Same catalyst will speed both the forward and reverse reaction. You see that when it goes from means forward reaction from reactant to product, this way it goes, and from product to it goes to this reverse way, but catalyst is means reducing both the activation energies. It lowers both the activation energy, both forward and backward. Okay. Their presence may change the rate expression, that is something else, but lowers both the activation energies equally. It lowers both the activation energies equally. Okay. That is most important. The free energy change does not depend on the path. So, the position is not changing, reactant and product. So, this is the free energy change, it is not changing. So, this is a thermodynamic parameter. So, but what is the reaction products that are not thermodynamically favored, the reaction products that are not thermodynamically favored cannot be formed by a catalyst. This is very important. If some reaction is not possible, whatever catalyst you give, it will not be possible. So, once the reaction is possible, then by using the catalyst you can make the reaction faster or slower. Thus, the role of catalyst is to speed up the reaction which are thermodynamically allowed. The reaction should be thermodynamically allowed, but by applying catalyst you can change the speed or rate of the reaction. This is very important concept. Now, enzyme as a catalyst. In our body system, I told you there are many enzymatic reactions are going on, many free radicals are generated, then free radicals are destroyed, all those things are going on, there are many millions of reactions are going on. But enzymes, you know, enzymes are very good catalysts, they are protein molecules having large molar mass. Okay. They are very complex structure, active sites are there. Okay. There are many active sites like this one, see here, this is the active site. So, here active site, you know, particular substrate can come here and fit itself. So, here there are two things, you see red one and green one. So, it can fit and the reaction goes on here. Okay. And then after the reaction they are separated, they are cleaved. So, reaction is going on in this active site. Okay. They are very good catalyst and very mild conditions, under very mild conditions they can do the reaction. This is another thing, and they are very selective also. There may be many compounds there in the system, but only particular substance will come here in the active site and do the reaction. Okay. That is very important for enzyme, very specific. Okay. In these sites some molecules can be accommodated, but most others are not even if they have similar structure. Maybe structure is very similar, but still they cannot be accommodated. There are many factors, size factor and functionality factor, there are many things. So, they cannot be accommodated. Okay. Now, so if they are not accommodated, then catalytic effect will not be there for that other substance. Okay. Now, there may be some molecules, in some cases a second molecule can bind itself to the active site of the catalyst, thus preventing the catalyst action. This is called inhibitor. Sometimes the activity is lost because of the presence of some other compound, foreign compound and then the activity of that particular place is lost. Okay. So, this is called inhibitor. Recently many catalysts are being designed. So, the design and synthesized many catalysts which are not enzymes, but other catalysts are being designed and synthesized. These are efficient like enzymes, means this is the synthesized catalysts, okay, but they have the similar properties of enzymes and can bring about reaction selectively. So, this is not enzyme, but synthetic compounds, synthetic catalyst, okay, but their activity is similar to enzymes, that is done. Now, you can see I have given some examples, you know, adipic acid and sorbitol, they can react to form a polyester, okay, polyester, and they are lipase which is an enzyme that can act as a catalyst in that particular reaction. You know, polyester, it is very important in textiles and many other purposes. So, it is lipase is the catalyst for that particular reaction. Another example, glycerol plus fatty acid, okay, triacyl glycerol, here also lipase as the catalyst. Sometimes these enzymes are also immobilized on some solid surface, okay, so that it can be recovered easily. So, that is also a very good enzyme, but supported enzyme, okay, that is also very good catalyst. So, there are many awards also, if you can develop something, green chemistry award, academic green chemistry award, all those things are there for catalyst development. And if they are very green catalyst, then it is again better for environmental purpose. So, this is biocatalyst. Now, the references you can read this all these are same references. This book again I am mentioning, it is really nice book, and some figures also I have drawn following this book. So, you can read this book to get better idea. And you have seen. So, in this lecture what you have seen that how we can explain the homogeneous and heterogeneous catalysis and enzyme catalysis, and what are the mechanisms that is happening there, and what is the activation energy, and how the catalyst behaves. Those are also elaborated in this lecture. Thank you.